just clarify those doubts through a foundational lecture on cobots, first of all. So what exactly is a cobot? So today, as we go on, we'll discuss what is a cobot, what are cobots, incident report, few incident report, why at all it is required, first of all. Okay, so those things we'll discuss. If you want, you can pin this uh, lecture so that everybody can see it. Maybe I can spotlight for everyone. Would help.
Yes, we are doing.
Okay, I am doing it. Okay then. So what is cobot? What are cobots? Incident reports. Why at all it is important? Different level of collaboration. We'll discuss on that. What exactly is a collaborative work? When we say a robot is collaborative, so how much collaborative is collaborative? Okay, safety standards, various standards that define cobot. ISO standards in particular, ISO 10218 2025, most recent one. Its adaptation in various countries, collaborative modes as per ISO standards. What is power, force, limiting, quasi-static and transient contacts? Why this is important? This is important to understand the difference between the current day cobot and traditional robots. Okay, biomechanical limits for the onset of pain, how that is defined, that is very important when we talk about human robot collaboration. This is very important, right? Example applications you will see, through which you will understand what is constrained motion, what happens when robot actually collaborate with human. There are constrained motion tasks also. It is there with traditional robot also. Not all, yes, quite a lot of them are already. So evolution, a brief timeline. Here you will come to know how India has evolved, where we have left and where we are now. Hardware difference, joint. What is the difference in the hardware when we make a cobot, or how it is designed? Control schemes, what difference is there? Cobot mechanical arm design. So these are fundamental technological difference. As we go on, we'll learn that, right? Yes. So this is there, and distinguishing features of cobots. What distinguishes that? Teaching through lead through demonstration, force control applications. Some of the videos I'll show today, which will help you to understand the task better. Okay. Let's continue then. Just a sec. Yeah. So robots, traditional robot arms and cobots and humans. So how that was defined? So cobots are collaborative robots that is designed to assist human by collaborating. Collaborating, that is designed to assist human. Earlier robot was also there, which was assisting human, right? But now the things are little different. We'll talk about various ways it can collaborate with human in the workspace. Not just it is collaborating, right? And cobots are intended to interact directly with human within shared workspace and in close proximity. So it is earlier days, no, all the robots were caged. If you know, you had limit switches at the gate. As soon as you open the gate, the robot used to stop. Or maybe some light curtains are there which sees how you are coming. There may be proximity sensor or velocity sensor for incoming personnel. So as you approach the robot actually slows down with certain velocity and then finally stops, right? So that is there. And then cobots have evolved as a more compliant form of industrial robot now. Okay, the industrial robot which we had earlier, the current day robots are very much compliant. So what exactly is compliant? Dictionary says compliance is the ability to conform to the will of others, right? Let's say you are shaking hand with a robot, so it is no more stiff, right? It doesn't do robotic motions, right? So they are very compliant. They respond to external stimuli. So external forces here. So if at all you are heavier, means you can govern the motion. You can govern the motion, and robots follows. Okay. So that is the way it is, and robots are inherently collaborative, right, are not inherently collaborative, right. So there has to have some kind of hardware difference which actually makes this happen, okay, the way they are controlled. So otherwise they are non collaborative. The collaboration is determined by the design of the application system. This is the um, current day robotic definition, collaborative robot definition, ISO 10218 2024 only it was released. So it says it is not only the way you make a cobot, definitely that is prerequisite to convert a robot to a cobot. Otherwise, also the robot has to be defined by the way it is applied, right. Cobot nowadays with a payload capacity of as much as 35 kg payload. So yes, it has inertia, right. If it hits a human, it can cause severe damage. Right, so that should not happen. So in order to take care of that, it is not just power force limited. There are many other sensory features which allows you it to be defined in a cobot category. So will things will be more clarified later on. So robot as such is an automatically operated machine, as you know, that replaces human effort. So replaces human effort, not human. Got it. So that is the first difference over here. Okay, it replaces the human effort, not human. And secondly, it may or may not look like human. So with or without any resemblance to human. Got it. Let me just go away. Any resemblance to human. So they are usually programmable through computer and can carry out complex series of task automatically. So yes, they can do multiple tasks one by one. They are programmed in a way so that it has some sort of intelligence. They are electromechanical machine. All these are fine, but they may not look like human and they may not replace human at all, right. And it replaces human effort. So that is to be noted. So this was traditional definition of robot. Apart from that, this additional definition says how a robot is to be made collaborative so as to be called as a cobot. So we'll see as we move on. Right. Let us just go to maybe this particular website, OSHA. Okay. So I'll just key in here this OSHA website. Let me see if I can open it. Yeah. Yes. I'll just change my screen share now, or maybe I can just share another window. Right. Yeah, if you can see this, this is the website of OSHA, that is Occupational Safety and Health Administration, official website of US, right, where they have totally means listed all the accident reports which were serious, and quite a lot of them were fatal to an extent when employee dies. Right, so that is what is fatality here. So this lists all sort of accident reports. When you see employee dies from chest injuries when crushed by a robot, you see robot can crush, right. And again you see there is another accident, employee is killed when crushed by a spot welding robot. Multiple injuries has happened by when it is struck by a robot. It may be struck, it can be crushed, it can be pinched, right, it can be trapped. So four different kind of things can happen. You see there is pinned. Pinned means you cannot move, you are clamped between the robot or robot environment, right. You may have got struck, means you are stationary or you may be moving, you are struck by the robot, or you may be crushed by the robot. So it's a advanced form of pinning later on. So these are few accident reports, not just few. You see, there are hundreds of them which are already listed on just US site. So it is not so nicely reported in India, but yes, there is incidents at Manesar plant in Maruti, which relates to that only, which was published in Times of India earlier. I have cut piece of that, maybe I can share later. So hope you understood it. So robots can kill people because they are brute machines, right? So they can kill people. So, so you got it, right? So this is what is listing of all. So you see, all the accidents clarifies your doubt, right? Why we need such robot which is to be compliant, which are to be differently defined and implemented so that it doesn't cause any human damage. So that is very important when robot is in human workspaces, maybe in the medical, elderly care, or maybe child care, nursing, right? When it is there in domestic spaces, hotels, right, conferences. So robots work around human, right? So it cannot be that you don't define your robot well while it is put to use. So this is the reason why cobot is necessary. So why do we need it? First of all, to avoid accidents as we have seen just now, due to impact, due to collusion, right? Pinching, crushing, or trapping. So these are few ways in which a robot can do kill a person. So there are a lot of accident reports which were reported earlier, as I have shown you earlier. Okay, so the side picture shows some experiments on a dummy which was done. So different areas of human were defined where it was hit by the robot and a study was performed. So I'll discuss in detail what was this study all about. So compliant task, again, it is ability to conform to the will of others. As you want, robot can go. You can shake hand with that. It is no more stiff. It is inverse of a stiffness. Compliance is inverse of stiffness. So it is required for assembly task. You know how you insert a key in the hole. If you remember, what you do? Even in the dark, you can insert a key in the hole, right? How do you do that? You just go there near the hole, approximate location. You just move your hand, right? You just move your hand, and while moving, you just monitor your forces. You monitor the forces, micro forces, and then you adjust your motion accordingly, or it gets adjusted on its own due to the constraint in motion. Okay, finally you keep applying a vertical pressure and it gets inserted. So that is how it is done, right? So again, surface finishing task, grinding, polishing, deburring, buffing, right? So all these tasks, when you do surface finishing, it requires a kind of compliance. You can move it. Let's say you are wiping a board. What do? You move on the plane, but you are constrained. You cannot get into the board, right? So that is a kind of polishing, rubbing off your board. So that is what you do, right? So this is how you control the forces in a vertical direction, whereas you control position in rest of the two directions, right? So that is what is compliance. Okay. Next comes is cooperative manipulation, right? So when you, let's say you want to take a cot from one place to other, two of you, your roommate and you are holding, other one is driving you to the next room maybe. So he becomes the master. You just follow the path. You may or may not be watching the path, but yes, you can feel the forces. You are vertically rising it up, right? Whereas along xy plane, you just follow the forces, you follow that person, you can reach to the other room. So this is how you do cooperative manipulation. These are not just short statements. I'll show you some example with more precise definition of constrained motion, right? Human robot collaboration. Human and robot can collaborate. Robot can collaborate, right? So same way, so human robot collaboration can happen in a similar manner, right? So safety of the robot and its surrounding environment. So it is not just for collaborative tasks to be performed, but for the safety of the robot and the environment. Environment here I mean the objects, the surrounding of the robot, everything is an environment. So the pictures here belongs to the DLR, that is German Aerospace Center. Human robot collision study was done. It was published in IEEE Spectrum in 2010, right? And these pictures are from that. This study was documented in a nice way as an ISO standard also. That is what we are following now, and it was put as an ISO standard, right? So that is what. So then let me just show you a few videos which may detail you what exactly is a cobot, right? Maybe through some of the applications here. Okay, just a sec. Okay. So you just watch this one. So what is happening here is a coordinated manipulation. It is done by robots, not a cobot in the industry. But yes, it is, all the robots have overlapping workspace, right? Automated robots are caged, you cannot enter, right? Robots are individually programmed through cell simulation. Collision avoidance is checked beforehand. Collision safety devices are there, right? So this is how this collaborative task is performed. This task is collaborative. Robot is not a cobot category, right? So the way it is applied, so it is a spot welding application. Again, multiple robots are caged. Again, you see two robots are handling a single chassis, right? Multiple stiff robot arms. These robots are again stiff robots which may have payload capacity like anything, right? So they are giant robots, but still it may be a cobot application because you have cooperative manipulation when two robots are handling one single object. So yes, they may have some force sensor, they may have some external compliant grippers which can take care of any uncertainty in the trajectory while it is moving. Got it? And this is the scenario in industry where you see there is no human around, right? And this is what we are preparing you for, right? This is the scene going to be in the industry. Collision safety device I just talked about. What exactly is that? It is a compliant device fitted at the after the gripper of the robot. Okay, after the flange and in between the flange and the gripper. So there is a compliant device fitted at the after the gripper of the robot. Okay, hope I am back.
Yes, sir, you are back.
Okay, is the video still visible? Okay, anyway, so this is an axial load it can take up, it can take moment load, twisting load, it absorbs shock and vibration, right? So this is by ATI, an US based company. It is taking up vibration while it is moving. So there is a limit switch which is triggered when it is colliding. Okay, if it gets collided, it sends the signal to the robot, now you have to stop. So this is the kind of in between device which stands in between the flange of the robot and the gripper, so that if it hits, it can take care of any collision, right? Further damage due to that. Okay, handling flexible objects. Either your robot has to be compliant, or the object which you are handling is compliant. Somewhere it adapts to any uncertainties. So that is what is the idea. So over here you see this two robots are stiff robots. Again, it is handling a flexible object. It is battery terminal. Okay, it is inserting it. So the robot is, it can move the, it is flexible object. You saw it is able to bend it. Coordinated motion, right? You have two robots. Your object is flexible, right? Robot may be fitted with a 6-axis sensor, 4-stalk sensor before the gripper. Again, robot can have external force control loop. It can sense the force, and you have programmed the robot to take care of the forces so that it doesn't do any damage. So these two are Denso robot, which are a stiff robot again, but it is fitted with compliant 4-stalk sensor, and it can take the values of the forces while it is working. So you can make the end effector active compliance. End effector is compliant, not the whole of the robot is compliant, right? So this way you can do such compliant tasks. Multiple robots can handle the same object. This is sequential collaboration. When you have human doing few parts, robot does something, automation does something, you may have another robot in the workspace that does something. So this is sequential collaboration, right? So automatically it is a bottle which is to be filled with a cap to be put and dispensed. So human poured in all the bottles in a bin. Robot picks up one by one another bottle, another one takes the charge and dispenses it outside. It's cooperative manipulator assembly. So this is pure compliant robot when you need compliance. This is assembly task, right? When one of the robot holds the object, other one inserts it, right? It is the gear shaft which is assembled. Responsive collaboration. Both the robots are compliant throughout. Dual arm with impedance controller. Reference trajectory is generated through teleoperation, right? And both the robots holds the object the way we do it with our arms. Got it? Level of collaboration is increased one by one, right?
Excuse me,
Compensating
sir.
object. Yes,
Sir,
you
what
said.
do you mean by the trajectory is created by teleoperation? Like, is it controlled by humans?
Yes, what happened, in this previous one now, both the robots was just, it knows that it knows the target where it has to be kept, okay, and doing so it just compresses the object so that it doesn't slip off, that's all. Whereas
Okay.
the trajectory how it will go to that place is decided by a person sitting outside the cabin, and he is guiding it. So essentially he is not holding the object through two different joysticks, rather just one joystick is taking the charge and transferring the object from one place to other. So two arms holding is done automatically, whereas the trajectory is planned through a remote teleoperation. This is from one of the publication which is there. So it was reported there. It is not directly evitable from here. Okay, so that is what. So this is
Understood,
how
sir.
it is done. And then you are compensating object dynamics. First of all, it has to compensate against the gravity. You have some payload, 4 robots and a human is doing the job, right? All the robot guides is gets guided by the external person. Object can be 3 kg, it can be 5 kg, 9 kg. As the weight changes, the dynamic changes. You saw this. This is again from a publication. I will note down all the publication which are from where I have picked this up. This is process automation, PCB testing. It picks up the PCB, puts it to the clamp, right? Switches on the knob switch, switches on the driver, and then PCB is getting tested. If it is passing, it keeps in one place. If it fails, it keeps into other place. So this is a PCB testing, electronic application. These are soft grippers, which are specially designed. They are compliant. Robot is compliant, so that if it hits anywhere, it. So if you remember, these are ABB dual arm Yumi robot. Okay, and then here this automation was done by Sony for Raspberry Pi board. Quite a lot of you already know it. You see how that assembly is being done. What are these? These small little things are PCBs. Right? There are different components which are placed one by one. This is USB stack which is being placed, a network stack. It has placed RJ45 jack socket. It works like human. So now it is constrained motion task. This purely requires a force control kind of task. What type of task is this? You see, this is a buffing task. When you are sanding the wooden door, okay, you want it to be polished later on, maybe painted after this. So what you do, you maintain a constant normal reaction against the surface. Okay, whereas you are free to move along xy plane over the plane of this surface, right? Not exactly free, some friction is there definitely. Robot maintains a constant reaction force against the surface, right? And from the side it is doing polishing, grinding, buffing, right? So again it is maintaining a constant reaction force. So this is the red one is the uh, emery paper kind of. Okay, what is this? This is constrained motion task again, when this is a door which is getting opened by the robot. So you don't know the axis of this hinge. Okay, hinges are there which is holding the door. You don't know the axis. So without knowing the axis, if you open the door, what will happen? You can take away the knob, right? It will break the knob, because if the robot is stiff, what will happen? You have a trajectory which doesn't match with the actual trajectory how it should be, because you don't know the axis of rotation, you don't know the trajectory, right? So what will happen? It will simply break the latch or the hinges, right? So that uncertainty is trained here using machine learning technique. This person continuously changes the location of the door, and every time it is successful. So it is a learning based thing. So you need to have some training which is to be done here. So it is advanced, more advanced. So as you go on implementing cobots, so you need to use this kind of thing. Okay, so let me come back to the original slide. So this was some application video. So with this as a context, maybe I can now explain you better what is Cobots. So as per International Federation for Robotics, it defines 4 levels of collaboration which exists. First is coexistence. Alongside robot and human are on the within the same fence, right? Fence, shared workspace is there. Okay, there is no shared workspace. Okay, robot cannot reach till human, but yes, accident can happen. Okay, they are in the same fence, so they are just alongside. Next one is sequential collaboration, where human hands over something to the robot, robot does something, robot in turn finally transfer it to another human in the workspace. So all of them are in same workspace, and task is being done here sequentially, right? So this is another level. Third level is cooperative manipulation. When both are in motion, transportation is happening and robot does something on the objects. Both of you are working on the same object simultaneously. You are moving, robot is doing something, and maybe you are also doing something. So this is cooperative manipulation. Okay, and the last but not the least one is a responsive collaboration. Robot responds actively like an assembly task. Okay, like an assembly task. The last one in the video was assembly task. So if that is the thing, it is the highest level of collaboration. Okay, so here goes this. When you see most of the collaborative applications are of this type today, mostly coexistence or sequential collaborations. This is very common and safe, but going ahead with cooperation and responsive collaboration are little risky, right? Fenced was the oldest robot, so level of collaboration increases. Requirement for intrinsic safety features versus external sensors, they also increase. So as we go up, it is like this. Okay, so this is very, very important. So it is actually the feel of the environment, the way robot behaves with an external sensors makes it a cobot, not necessarily the construction of the robot itself. Okay, we'll discuss some details later. So these are the few standards which actually defines a cobot. First two, first two are here, like this one. Okay, these two, that is 2006-42 EC. This is machine directive, European Agency for this is these two standards are applicable for any machine, including robot. Safety of machinery, general principles for design, risk assessment and risk reduction. You should know this first, right? Before you put robot or any automated machine in human workspace, you have to be very careful. Just a motor can cause accident. If it is having a rotating spindle, right, maybe it can pull your loose sleeves or maybe your hair, right? So safety of machinery, so general principles, right, for risk assessment and all is to be done, and that is done with ISO standard like this. So these two are machine directives, machine safety, which is industry standard, goes to cobot. Next two are for robot standard. Robot safety requirement. Part 1 is for industrial robot. Part 2 ISO 10218 2025. You see latest version came in February, and that also has got industrial robot applications and robot cells in particular that deals with cobots. So this details the application of robots in robot cells where human robot collaboration is also covered. So this is the latest one. Okay, so this applies to the robots. Okay, and the last two standards are only for collaborative robots. 15066, 2016. 2016 is the year. Robots and robot devices, collaborative robots. So these are few standards you should look for when you buy a robot, maybe you use a robot. You should be aware of these standards. How safe is my robot and my workspace is, because you are going to enter a workspace which is deadly automated, right? They are very, very dangerous, right? So these standards should be well known to you. Okay, and if at all you are buying a robot, you should look for whether my robot covers all these standards or not. If it is not, maybe the vendor is fooling you. So it is very important for teachers, very students, for students who are going to pass out and be maybe robotists or maybe in the robot environment. Even if you are a maintenance engineer, you may not be a robotist, but you are in an automated workspace, so you should be aware of these standards. Two for the machines, two for the industrial robots standard, last two is only for the cobots. Right, so this is apart from other industrial standards like ISO 9283 that details about the repeatability accuracy of the industrial robot, and 13849 that says safety of machinery and all. Right, so these are important standards to be noted. Look at the data sheet first and then compare your robot whether it has all these features or not. So this essentially 15066 has got many adaptations, and ISO 10218, right? So this one has got many adaptation later on. So in different countries they are put with different names, but they are all the same. They are adaptation of ISO 10218. Earlier it was 211, which was old, now 2025. That is the latest one. So, and it keeps changing. Okay, so you have to keep an eye, and their ISO standards are expensive. Maybe your institute has that subscription, or maybe your company has the subscription. Try to go through that first. its adaptation in various countries. So what it covers basically: hazard identification and risk assessment, design requirement and protective measures, actuating controls. So controls, what should be the feature in the control, that is also covered. Safety related control, system performance, how much should be the overshoot, what should be the maximum force it can create when it collides, robot stopping functions, speed control, operating mode, pendant control, teach pendant control basically, control of simultaneous systems if you have, collaborative operation requirements, singularity protection, that is very, very special. If you are into robotics, maybe you will learn it very soon, or maybe you have studied it already. Access limiting, movement without power drive. Okay, without power, in case of power failure, what could happen? Right, and provisions for lifting, electrical connectors and all. So all these are covered in various chapters of ISO 10218, and they all have equivalent similar guidelines in various adaptation across countries, right? So what it actually does, collaborative modes says safe monitored safe stop. Robot operates autonomously, pausing safely for entering personnel. It automatically, maybe you have a gate with a limit switch. As soon as you open the gate, there is light curtain or a gate switch that sends the indication to the robot, and robot gradually stops, right? Next one is speed and separation control. Robot adjusts its speed depending on the distance from the worker. If you go close, it will operate slowly. No contact with the robot is allowed. It uses vision, lidar or ultrasonic sensor. Right, it can detect the speed with which you are approaching the robot. Higher is the speed also, even if you are far off, but you are approaching fast, then robot goes slow. Okay, so they are governed by that. This is manual guidance. This is where actually all the vendors, they fool us. They just check this feature. Most of us can check it easily. If you can manually guide the robot, if you can drag the robot anywhere you feel like, so that doesn't mean it is a cobot. Using it as a high performance manipulator. It is used for teaching a robot. You teach a robot using teach pendant through joystick. Take the robot, teach the location, take it to another location, teach the robot, and now you say repeat. It will do that repetitive task. But this can now be done manually because the robots are soft. You can drag the robot using manual guidance, using it as a high performance manipulator. You can program it also. It may have a button. So this is to be noted. Sometimes the robot is not compliant. What the vendor does, basically there is a button. If you release it, okay, it releases the brake and you can drag the robot. But normally while execution, it may be very stiff. It can hit you hard, right? You may not be able to move it. So button to release the brakes, and you can drag it anywhere, but it may not have gravity compensation also. Okay, so those type of robot, any robot which can be manually guided, need not to be a cobot also. Okay, the last one is the power force limiting. This is the most important one. That is how your robot can operate. Safe human robot contact. It is force is verified. Okay, and power is limited. Power is limited. I'll just vanish for a moment. So cobots may have stiffness or impedance controller running behind. It is not only position controller, you also have a stiffness controller. How much stiff is your joint, how much stiff is your end effector Cartesian displacements, right? So that is how it is controlled. Okay. So now power force limiting, what is that? The last one, quasi-static contact and transient contact, what are they? So let us discuss these. The robot system shall be designed to adequately reduce risk to an operator by not exceeding the applicable threshold limits, values of quasi-static and transient contact. So what does it mean basically? Firstly, contacts could be intentional, contacts could be incidental, or maybe due to failure of the robot. Okay, what is quasi-static contact? Let's say you have a hand which is pinched between the table and the robot gripper here. This is my robot Yaskawa here, which is a 12 kg robot which can run at least 2 meter per second, and it has a repeatability of 0.01 mm. So you see it can literally damage anything. Right, although it can carry just 12 kg payload, but they are very stiff. Okay, so what is quasi-static contact? In this case, contact duration is quite long. Limiting criteria, peak pressure and the forces, that is the stress which is generated at your hand. Body gets clamped between the part of the moving robot and another fixed moving part of the robot cell. So you are clamped between the robot and the environment. So this is what is a quasi-static contact. Contact duration can be very long. You don't have any way to escape out of it. The second one here is a transient contact. Contact duration is less than 0.5 second. Limiting criteria is again peak pressure and forces. Right, energy transfer. Energy is transferred to your body due to the motion, due to the momentum of the robot. Energy is transferred, right? The body may recoil, you may escape, right? You can retract from the moving part of the robot. You are free to escape. This is a transient contact. In this case, there is not much of damage which can happen, right? But yes, there is always a possibility. So how that is defined in ISO 15066. So it is also defined, same study, the robot collision with human, that study was done. So it is part of that. These values are estimated by 3 repeated tests on 100 healthy adult subjects. Project report is here, University of Mainz, Germany. Right, so this work was done. It was later on put as ISO standard, and that is how it is done. So collaborative operation is from here till here. So onset of pain starts here. You may feel little bit of pain, but definitely you are not injured. So that is the threshold for injury. It is very much subjective because every person has their own feeling and they may get injured plus or minus, but yes, these are average of over 100 healthy adult subjects. Right after this, injury can happen. So injury can be major, it can be reversible, it can be irreversible. Minor injury or maybe a simple bruising or cuts, right, reversible. Reversible, you have a broken bone, but yes, it can be recovered over time. But irreversible, there may be some amputation which has happened, right? So that is should not be there. So these are kind of injuries which can be there. So this standard 15066 especially says how your robot should be, like quasi-static contact, it has defined already. So maximum allowable pressure is 110 to 300 Newton per centimeter square at 29 body areas. I'll discuss about that also. What are those 29 body area? And allowable forces are, force is 65 to 220 Newton. Okay, for transient contact, it can be 2 times of what is for the quasi-static contact. You can take up little more load when you are in transient contact, right? It is for a shorter duration. Okay, so these are different body areas which was studied and put to 15066. Okay, so that excludes head areas. So no experiments was done on head areas, head and forehead and skull area. So again, two points are there: face, neck, shoulder. chest, abdomen, pelvis. So this is all different areas which is defined. So you see, so much of detailing has gone into making of a cobot to put the robot alongside your human workspace, alongside the human in the workspace, right? So you see, so much of study research has gone in. Then there are plenty of improvisations which were done before it was actually put to use. So these are some of the constrained motion tasks in which I have shown a robot writing on a blackboard or a whiteboard. So what essentially you can do, any body in space has got 6 degrees of freedom, right? You have 6 degrees of freedom. So what can happen, maybe when you are wiping a board, what you can do, you can move on the surface whereas you cannot get into the board. So you are locking three different degrees of freedom, you are left with three. So that is what, wherever you are constrained, you can create forces because you cannot get into the board. So you can create forces in that direction. If you cannot rotate, that means you can create movement. If you are free to move, you cannot create any force or a moment, is it not? So that is what. So when the robot is moving on the plane, it cannot create any forces, so it can write on the surface, but it cannot get into the board. It is constrained and it generates a normal reaction force perpendicular to the board, right? So this is constrained motion, right? It is moving. Again, opposite constraint is when the robot is inserting a pellet inside the hole. So as soon as it gets inserted, what happens? You cannot move along these two directions, x and y. That is, if this is x, this is y, you cannot move, but you can go vertically up and down. You can move like this, is it not? So z axis you are free to move, you cannot create forces, but x and y you can definitely create forces along these two directions. So it is constrained along xy, free to move along z. So this is again constrained. Okay, different types of constraints are there. This is translational constraint. Next one, any task like exoskeleton or a vision based task are not very accurate, right? So when it is any object that you see using machine vision, you are not very sure whether that object actually lies there. So there may be some inaccuracy in the doing something while you actually perform the task. So in case of robot, if it is stiff, so it may hit the object and it can damage the object, right? So if you cannot see properly, that means you need to have some sort of compliance in the system, right? So in that case, what will happen? So you need to have some sort of compliance. So if it hits also, it won't damage much. Next could be a exoskeleton task. When a person is donning a exoskeleton and commanding the robot, your arm is a 7-DOF system. You have a spherical joint here, you have elbow joint here, you have spherical wrist which can go roll, pitch and yaw. So altogether 3 plus 1 plus 3, you have 7-DOF system, and it is mapped to a 6-DOF robot. Again, these are not very much matching, but there is a human in a loop. If you cannot see properly, you cannot execute such motion. Okay, so here a person is seen commanding a robot, industrial robot, using that. Again, the robot should be very compliant, otherwise when it hits, it can damage the wall, right? In on this table you can see there is a glass plate here. So if it picks up from that glass plate, if it hits that glass, it will be broken, right? Next one is a teleoperation. A person can see everything in a 3D screen which is in front of him. He is wearing a 3D glass, black colored, and he is using a haptic device to command the robot. What is an haptic device? Haptic devices are devices which can do position commanding to the robot. It can command for 6 degree of freedom motion, but it can also feel the forces which is felt by the robot. So what essentially it has a force torque sensor which is sitting here. So whatever forces are seen by this while picking up these pellets on the table, okay, so those forces are reproduced here in this haptic device. So it is a joystick and it can make you feel the forces. So for doctors, they do teleoperation surgery using this. They know what they are cutting. They are cutting the tissue or they are cutting the bone, right? They should feel the force while they are moving the robot, right? So they are trained so nicely that they can understand such minute changes using machine, right? So that training has to happen. So this fellow is trying to use a Novit Falcon 3-DOF device, haptic device, to take up a pallet, insert in a hole, and this one is trying to move the robot in workspace using a haptic device. So both are using haptic device. So constrained motions should reflect some kind of forces also to the device. So next one, you see there are four different instances when the motion is constrained. First one, this one is opening a door in which you have a constraint, like you have an axis about which you can rotate, right? Your robot, if it is not compliant, that means it cannot take up any forces due to any error in the trajectory if it has calculated. So it has to go in this trajectory, but if at all there is any collision or there is any inaccuracy in the calculated trajectory, it will break the door or door handle or the hinges, right? So that should take care of any interaction forces due to any error. Similarly, this is a drawer, right? The next picture is of a drawer. You are trying to open the drawer, it has to move in a straight line. You don't know where is the straight line, but you can do it. You can just pull it out, and whatever is the interaction force that come on the robot due to any error in the calculated trajectory while you were pulling it out, so those forces will actually make use of your robot compliance, and it will do the job. Right? So these are the reasons why you have to have some sort of compliance somewhere in the robot. So earlier days, people used to have maybe end effector fitted on a spring-like structure. Okay, so any uncertainties were taken up by by such. So writing on a board, you have already seen, pushing a button. Again, you need to create normal reaction against that, and you are free to move along remaining two directions, right? Again, rotating a knob switch, right? You can rotate about this but cannot rotate about other two axes. You cannot move along any two other axes also. You cannot rotate along two axes, you cannot move along another two axes. Four are constrained, right? So this is again a constrained motion task. These are all constraints which are there in day-to-day job that we do. That is the reason why you have a cobot. So let us just see the timeline, how it has evolved over the years. I don't have much time to go through each one of them, but these are some, the red ones I have indicated. It has started with passive control when you don't have any force torque sensor, but you had spring-like structures fitted at the end. Then you had rest force torque sensor over here. Later on, impedance controller was inserted, external force control loop was placed, hybrid impedance control was done, adaptive thing came up, direct drive joints that came up with ABB, right? This series went on, and finally now we are using AI and ML based technique, deep neural network reinforcement learning based technique, to take care of the forces intelligently, right? Because now robots are doing complex tasks, not just industrial tasks. When they are in human workspace, it is like that, right? So there are many approaches to that. Just maybe if you are already recording the talk, maybe you can refer them later. I'll share all these also. Okay, so this is how we progressed. We started from passive. We had some kind of active with force torque sensor. Right, later on we developed over algorithms to handle those senses. Then we came up with intelligent machines, and finally most advanced machines came up. Okay, so this is how we went on. Okay, just a sec, maybe I have some videos also further. Okay, so now how it all evolved, you see the first thing to be noted here, in 1990 Dr. Prasad Akela, PS from IIT Madras, he was an engineer in General Motors. Okay, he led the team who built world's first cobots for material handling in his company. Later on, it was patented by Colgate and Peshkin from Northwestern in University, and it went ahead. So you see, some Indian is there somewhere in 90s. We are talking about cobots now. The first US patent, it came in 1997. Okay, the company called Cobotics, started by Colgate and Peshkin in 97. 2003, it was acquired by Stanley Assembly Technologies, and follow-ups. Now the patent has expired already. So quite a lot of companies have now poured in their technologies. First one, the pioneer, were the German Aerospace Center DLR, which was later on adapted by KUKA LBR-3 lightweight robot. Now it is IVA. Universal robots UR5, 5E, UR12. So many variants of UR robots have come up. Fanuc, they have come up with the heaviest payload capacity cobots. ABB Yumi, you saw in working, doing assembly for your Raspberry Pi boards, the video that I showed. Rethink Robotics, Soya, and these are the companies who followed up in human workspaces now. These were from industry. This is how it has evolved. Right. So videos I have shown here, maybe I'll show it now. What kind of task normally a cobot can do? Okay. Let me just see if it is here. IWA capabilities. Just a sec. There are some bits of pieces of videos are there. Maybe I'll directly share the screen totally, whole of my screen. Uh, I hope I have some time. Okay, so yes, I don't know if you can see this. This is a kind of motion which is gravity. You can see this. Hope you can see this video.
The video has not opened yet, sir.
Viewer is not open. Just a sec. Let me try. So if you see this, what exactly is being done here? I'm able to move this Kuka Iva robot, which is a 7-DOF robot. So as soon as I set it in compliant mode, see, I am able to orient it in any manner, right? It is free to move, is it not? It is fully gravity compensated, but position is controlled. It is not changing its position, but I can orient it in different manner. I can change the orientation, but I cannot change the position of the tip. Okay. In the second video, I'll show lead through programming. Okay. I'm able to drag this robot and touch upon various points on the surface. Right. This again is Kuka Aiva. It is at IIT Delhi now in the controls lab, electrical engineering department. Earlier it was in the mechanical engineering department. The previous video was from Kuka, Gurgaon, the Kuka center. They have a training center there. So I am taking it to different location one by one, teaching those locations. So at the end, I have just left the robot, asked it to repeat it. This is known as a lead through programming, teach and repeat kind of. Okay. So earlier it was very difficult task. You have to manually jog it to different location. Now you can do it in this manner. Got it? Null space. This is a special kind of job which is there where you can move the robot in its null space. So it is for the same orientation you have infinite solution and the robot can move in the null space. These are some advanced concepts which are covered in my course Collaborative Robots, which is to come in the January session in NPTEL. So yes, you see orientation and position is not changing. It is behaving like a compliant robot with some stiffness, behaves like a spring, but the arm can be rotated. Got it? So this is the beauty of such kind of 7-DOF robot. This is the front view of the same. This is me doing this. You see, the position is fixed, right? End effector flange is fixed. I am able to take in the advantage of infinite solution of a 7-DOF robot, right? So it has programmable compliance. You see in this task, what happens? It adapts to the surface. That is what is shown here. The robot is made to follow just horizontal straight line, maintaining 10 Newton force on the surface. So vertical force is maintained while the robot moves from left to right or right to left. Okay. It follows the shape, right? In between, if I move the table also, the path should change. Now I am showing the stiffness, it behaves like a spring. Right? All these experiments are performed at Kuka Center, Gurgaon. I am moving the table, but still, you see, it is able to follow the trajectory. Got it? So it is not a taught positions which are followed. It just follows, maintains a constant normal reaction force and follows, goes from left to right. Right. So this is how it can be programmed as well. So these are some of the things. Orientation, stiffness, null space, lead through gravity, full gravity. Arbitrary reference compliance, what it is, let's say you have a tool which is fitted here. So currently is this point about the white center point, it is able to move. Okay, that is the flange center point, which is stationary. But I can change that point to the tip of the tool also. Now it is that. So tip of the tool is stationary, rest of the robot can move. Got it? So you are changing the reference center. point, right, where it is compliant. So these are a few demonstration which demonstrates these technology transition which has happened over the years and made this happen. What is the fundamental difference which allowed you doing all these? Okay, so traditional robot runs on position mode. If you see a pendulum here, it has a joint position sensor over here. Okay, while it is moving from low to up, what happens? It continuously keeps checking what is the angle here. Okay, as soon as it reaches the desired angle, commanded angle, maybe 30° from the vertical line, okay, 30° from here, it will stop. It has to keep checking your feedback angle. So it is angle control. So if at all there is any obstruction in its way, okay, so what will happen? It will try to build up the forces so as to overcome those external obstruction and reach to the commanded angle. So that is where it is very, very dangerous. It works on position error, velocity error and integrated error over a period of time, commonly known as PID, PID controller. So if the error remains there due to the obstruction, okay, if the error remains there while you are commanding it to go to 30°, there is an obstruction here, error will remain there. So error integrated over a period of time will build up too much of torque over here, and that will burn the motor or maybe break the obstacle or maybe the robot arm or something. So this is very, very bad. So you were running on joint position servo control. Now the idea has changed. Okay, the new robots, they run on position controlled servo, that is fine, with torque limits. You cannot go beyond certain torque. Either it will safely stop or maybe it will remain there, right? Or it is purely run using torque controlled servo. Let us say you have a rod of mass m. So what will be the downward force? Will be mg. If it is at any angle theta, so you have mg sine theta, which is the driving force. Mg cosine theta basically creates reaction over this joint, right? So that is not going to play any role in moving it. So mg sine theta into L by 2 is the torque at this moment, is it not? So effectively it is mg L by 2 sine theta, is it not? Tau is equal to mg L by 2 sine theta. This is basic physics. So in order to be at 30°, it becomes sine 30°. So it is mgl by 4, is it not? So mgl by 4 torque, if you have provided, it will precisely go to 30°, not more, because to go more it requires more torque. So any obstruction in its way will stop the robot. It won't accumulate over period of time. Torque is limited already. You are running purely based on the torque command, not on the position command. So that is what is the latest robot all about, and it is run by joint torque, which is calculated using inverse dynamic equation like this. This is the gravity torque. While doing any quasi-static task like slow moving task, dynamics are ignored and you run only due to torque due to gravity. And you continuously compensate against the gravity, and whatever torque is required to go to certain place, you just provide that. So any additional force created due to any obstruction in its way will not break the robot, or it won't break the environment, it won't do any wrong, right? So that is what is latest cobot. So what essentially you have is your joints should not just be torque commanded joint, not position commanded only. You can have a position controlled servo with torque limits, or maybe you can just command using the torque. So that is how cobots are designed. So you see the robot joint itself is very different. Okay, so joints are made differently. Okay, the controllers are different. You had this controller, now you have this controller which you have to follow. Okay, So now, how the earlier actuators were built, if you know the joint, a DC motor, this was the motor, this is a gearbox, bearings, and at the outside of it you have an encoder which gives you a feedback for angle, is it not? So you got feedback for angle only. So this supports doing only joint position control, not joint torque control. The actuator run with joint angular position feedback only. Output shaft uses high gear ratio for transmission to increase the torque output and reduce the angular speed. These gearboxes would reduce the speed so as to make it more controllable, and it will increase the torque output of these motors. Is it not? It has very poor load side to torque reflectance. So any torque coming here will not be visible to these currents in the motor. So that is poorly reflected. So that is why these are not safe. They are very stiff robots, right? It uses current based torque limits for safety. If at all current surges, it will simply trip, it won't control it. High gear ratio makes it non-brake drivable also. Okay, but in current day robot, which is a cobot, joints are built like this. Okay, you have joint position sensor, right? You have harmonic drive gear unit. You have torque sensor also. You can continuously monitor the torque and control the torque. You have robot drive, whole of the drive mechanism is here itself, H bridge or whatever is here only. You have microcontroller board, power supply, power converters, bearings and all. So this joint is very complex, right? So that is where is the cost. The actuator is run with the torque with position feedback. It knows where it has to go, but it controls the torque. Got it? Now the output shaft uses low gear ratio for transmission. This has very low gear ratio. So they are back drivable. Joints are back drivable. It allows manual guidance. I can guide my robot with ease of programming. Run with commanded torque inputs, right? And monitor the joint position for ensuring precision and safety. Free falling can be detected, over speeding and joint software limits can be placed. So this is the typical construction of joint actuators. Right? This is how it look like. They are literally very complex. This is what, so you use normally cascaded joint position controlled scheme for traditional industrial robots. You have torque controller inside, speed, position, and finally inverse kinematics commands for the position. You check the commanded position and the actual position, calculate the error, apply PID in position, generate the reference trajectory in joint velocity. Then you have torque commanding, finally the actuators are run. Somebody is from control can understand it. This is known as cascaded joint position control. Okay, but yes, in sake of time, I am just skipping it. But in case of um current day robot which has joint torque control, now you have encoder used for communication of the position, but internally you have PWM or inverter based, that is inverter based controller, which is also known as a BLDC, which uses inverter type of controller or maybe variable frequency drive controller for synchronous AC machine. Right, it has a current controller. Current essentially torque is equal to current flowing through the armature, right? So it is proportional to that. So it is motor constant. So torque is proportional to the current. So if you can control the current, you can control the torque. So that is how the target torque is achieved. Okay. So you command for the torque, it controls the current, and finally motor runs. So this is how, this is the current day control scheme, right? So they are lightweight, concealed wires, no wires are hanging outside, soft and rounded edges, right? inbuilt self-calibration system for mechanical stops, safety against pinching, trapping hazards as in these ISO standards, electromagnetic compatibility is there, they have immunity and emission compatibility, vision and shock resistance as per this ISO standard, IP ratings are there, ingress protection for dust and water, provisions for heat dissipations, all these materials they dissipate the heat out. Over here it is aluminum, okay. Humidity up to 95% non-condensing it can run. So this is what is modern day cobots is all about. Right, I think in sake of time I can stop here and maybe just this summary slide, I'll just run this one. Overall, this system, it looks like this. Okay, your current day system, it looks like this. It is the arm, this is the teach pendant, here is your hardware and your PC which is used to control it, right? And these are some quick references for major components which I have discussed: torque sensor, servo drives, frameless BLDC motor, harmonic drives, robo drives. So above list is not quite exhaustive, but yes, this should be quite good enough to make you follow my slide. Okay, that's all. I think I can stop here in the sake of time. I have many more slides, almost hundreds of them, but yes, now let's stop for the query. Hope you got the idea where how what different things a cobot can do, right? What different thing a cobot can do, right, as compared to modern day robot, how different they are, how are the control schemes are. So as such, it is an impedance controller which is working. Somebody from control may ask that. Okay. So yes, any queries you can definitely get in here. Acknowledgements to the videos that I have covered. These are a few videos which I have shown you today. Yes. So my special thanks to all these institutions: KUKA Private Limited, India Private Limited, Gurugram, Haryana, where all the experiments were recorded, BARC, who funded me while I was doing my PhD to do this work, DRDO, who is funding me now to work on humanoid, full-fledged humanoid of 14 DOF, at least 7 DOF on each arm, collaborative robots indigenously built, executed at IIT Dhanbad now, and definitely IIT Delhi, my alma mater, who has trained me to do all these stuff. Thanks a lot. Any queries, you can just see my YouTube channel also, where all these videos are already lying there. Thanks a lot.
Thank you so much for this session, sir. We are open to questions now. So,
Only 13 remaining. I see people are dropping. I know quite a lot of you may not be from robotics, but yes, as a sake of engineering, this technology is very, very novel and very different. You should have stayed there. Anyway, yes. Any queries here?
sir, what are the actuators that are used for torque control in industries? Is it just servos and BLDC motors?
It is BLDC motor, but you can do torque control also. I have listed it here. You can just see the synaptic and somanet circular. This is the driver. Motor is the same. You know, same DC motor. You can create a servo loop and make a closed loop in position. But if you measure the current and you can control the current, you can control the torque also. Right. So you can use DC current chopper drive to control the current. With the same motor you can do it, and you can use typical H-bridge driver with position feedback encoder and create a closed loop, and you can make. So it is the drive which makes the difference, right? It is not the motor itself. Motor is same, right? But the drive is different. Drive allows you doing torque control or current control, which was not there earlier. It was only position velocity control. Got it? So drive is different. So this is servo drive, torque sensor, frameless BLDC motor. So motor can be any motor. Yes. Yes, yes, please come in.
These these
So,
cobots are costlier than traditional robots, right? So they are costly.
yes,
They
they are
are
costlier.
very
You
costly.
see, lot of technology has gone into making of this. The joints are so complex, and the prerequisite you have seen, it has so many features, right? Apart from just taking a
Yes.
payload from one place to other, they are compliant. So that is the reason they are costlier.
Sir, is there any way that they can bought at a cheaper or
See,
at the
there
same
are claims
price as
actually.
traditional?
There are many industrial robot manufacturers who claim they are making cobot, but actually they are not. They are just making it compliant and showing it to you. Maybe you get convinced that yes, if I can move it like this with your arm, it is cobot, but actually it is not. It has to follow various industrial standards as I have discussed. No? So what was
Yes, sir.
that? So if it is not following those standards, they are not actually cobot. So all these standards it should follow. Right. So that is what is so getting these standard certifications, right? That also puts into the cost of these robots. Got it?
Okay, sir. Yes, sir.
Yes.
Sir,
There are
so
many
in India,
manufacturers.
sir, is cobalt achieved in India? Like,
You
are
tell me.
cobots are there in India?
Yes, there are. You can make one. You can make one. Technology is not hidden. If you can make a standard arm, you can make it a cobot, you can make it a robot, doesn't matter. Just try and make a two-link arm as your engineering drafter. You have seen your engineering drafter, put two motors and try to control the XY position. Can you do it? It is a two-DOF arm and you move it controlling the two joint angles. Okay, let me just go here. Let's say you have a link like this. Okay, you have first link which goes like this. You have second link that comes like this. Essentially, you are controlling this end effector position XY along this. So what you essentially you have to do, you have to control this angle theta 1 and control this angle theta 2. This is L1, this is L2. So simple it is. Just two link arm you can create it. If you can control the joint angle, if you just buy a typical DC motor, geared DC motor with encoder available
Yes.
anywhere in Robo or Amazon or anywhere, take this, make one, who is stopping you? Right. And then to make it torque controller, you use any chopper drive. Now you are using H bridge drive. You can use any chopper drive, you can make it. So commercially we have failed. Technologically we haven't. We know in and out of it. Few companies are there like N Motion, which is an outcome of I think NIT Calicut. NIT Silchar, there is a guru who has come out of one among you only. I think he's at currently at Chalmers University, Shivesh. He has worked with Kuka Aiva, worked with Kuka Aiva. He was with me as an intern when I was there at IIT Delhi doing my PhD. Both of us have a paper also together, journal paper, and then he went to that no Suratkal. He is currently at Chalmers University as assistant professor working on these kind of robots. So he is one among you. Just Google him. Uh, Try to contact, catch hold of him. No, maybe you can invite him for a talk, referring me that yes, Arun sir has told you to contact you. He is your senior. So nobody is stopping you. You can make one of your own, right? And don't try to go away just like him. Try to bring him back or take the technology into India. Technology is all there.
Uh,
Got it? Yes.
Excuse me, sir. Sir, how do you control the current in a DC motor? Like, is it even possible? We have been doing PWM control till now, but like, if we want torque control,
I'll tell you what you can do here. Maybe just a sec. I'll wipe it off. Okay. Current control. Very simple, very easy. What you have been doing so far now, um, this is your motor. Okay. You are running it with the current flowing through this, right? Like this. Okay. Now, additionally, what you do, you put a low value resistance here. Okay. Low value resistance here. This is R, small resistance, very small resistance, RS, small. Okay. And you measure potential over here. This potential will be proportional to the current flowing through this armature, is it not? Higher is the current, higher is the potential drop across this. Right. So this gives you the feel of potential difference, the current which is flowing through this motor. So as I have told, torque is equal to Km into Ia. Higher is the current, higher is the torque. So if you have to control this torque, you have to control this current. Correct. For good motors, Km is well known. It is there in their data sheet. If you pick up a Maxon motor data sheet, this value is already given in the data sheet. Right. So you know Km, that is the constant. Maybe you can find it out also. If you have a torque sensor and a current sensor, plot it and get the slope Km into Ia. Km you can obtain it. So provided Km is known, you just need to control the current. Current, you are measuring it through a value known as Vi over here. Right. This is the applied voltage. Right. Vi is there. So what here you can do, you can have a switch here. Switch can be a transistor switch or a MOSFET switch, right? So what you can do, you are measuring your current. Okay, you are measuring your current. It is increasing, increasing, increasing rho. So as soon as it reaches a value which is desired or maybe little higher than the desired one, correct? So if this is the desired current, so if the current goes beyond that certain value, you switch off the MOSFET. It falls down, current falls down. Again you switch on the motor if it falls below some value. So this is what is a chopper drive. Such an easy language. Today I have taught you what is a chopper drive, how that is done. You have a MOSFET switch here, right, which can switch on and off this motor. So you are sensing the voltage across a small value resistance, feeding it back to your microcontroller. Microcontroller can read analog input. If this voltage is very small, maybe you can put a small gain here and put it to microcontroller, analog input channel, right? You read this. So you can switch on and off this motor. Maybe you have a H bridge. You can switch on, switch off depending on the value of current it has. So if it reaches here, you switch on. If it reaches here, you switch off. You can do this now, current control. So if you are able to
Yes, sir.
regulate this current within certain limit, that means essentially you are limiting this torque. So this is how current chopper drive works, and you also can make it. So this is very simple, right? Position you can control by taking feedback, making a PID loop that you have been doing since long time, right? Velocity you can control by duty cycle control, by PWM duty cycle on H bridge, Cytron motor driver or some kind of DC motor drivers you have used it. You can do velocity control. You can direction control also. Flip the H bridges, right? Diagonally opposite one should be able to control the direction. You can control direction, position, velocity, and now you can control the current also. So you can do everything else. Pick up any motor, try doing this. These are very, very fundamental before you have to make a robot, right? Hope I am quite clear.
Yes, sir. Understood. I'll
Very
try
good.
that.
Yes, try and report me. Show me the results. I'll be very
Sure, sir.
happy.
Sure.
There is a company called N Motion. N Motion. They are students as old as you. They have just passed out, and they are doing it with BLDC motor. They have established their own startup company We have bought one motor, maybe we are in a process of buying it. DRDO has taken it. They are putting up stalls everywhere across India, doing well. So in India, people are doing it now, and they are one among you. So do it. Okay. Yes. Any other query? No? Then maybe we can stop here. Hmm. So yes, any other query maybe? So I'm stopping it maybe. Yes, that's all. Thanks a lot.
Thank
Thank
you
you,
very much
everyone.
for this, sir. Uh, I hope everyone got something fruitful out of this session. So thank you very much for uh, spending your time and effort to for both of these
And
sessions, sir.
for all of you, no, connect me over LinkedIn. Maybe I can answer further query. You can see all my videos there, right? And yeah, you can connect me on Strava also. I do regular running also, right? 5 kilometers every day. You can catch me there, right? So you can do anything with me. Okay, that's all. Thanks a lot. See you then. Bye bye.
Thank you, sir. Thank you, sir.